We know the derivative of sine, the derivative of cos, and now we know the derivative of tan is secant squared. So now we can apply all the rules, the chain rule, product rule, quotient rule, to these new functions. What would that look like? Oh, I started early. Oh well. So if you have this equation, the first thing you have to decipher is what rules are present. Should I use quotient rule, product rule? Is this a chain rule? We have to look, are functions inside of each other or are just functions multiplied by each other? So in this case, we have two functions multiplied by each other. So to find the derivative, we're going to use the product rule. What does the product rule look like? Keep one the same, derivative of the second one, and keep the second one the same, derivative of the first one. I think what makes the trig functions a little bit more difficult is that the derivative looks so different from what the original one was. We started with tan, now we have a secant squared. So when we look at this, with the plus sign in between, means that we could do the derivative of the first term and the second term separately. When looking at the first term, can you see that there's a 2x inside of tan? So the first term will be a chain rule. When looking at the second term, the 1 over tan x, we can either use a quotient rule or we can change this, and I think that's what I might be tempted to do. I might be tempted to change that to tan x to the negative 1, moving that tan x from the denominator up to the numerator. But then that would be a chain rule as well, because the tan x is inside of a power. So how do we do our chain rule? Take the derivative of our outside function, keep the inside the same. So for tan 2x, the outside function is tan, so the derivative of tan is secant squared. We'd get secant squared 2x multiplied by the derivative of the inside function, which is 2. Same thing with the second one. We'd bring the negative 1 out in front, which will just make a negative sign. Keep the inside the same. Subtract 1 from the exponent, multiply by the derivative of the inside function. One of the things that this really gets you to do is to manage a lot of data. You've got a bunch of rules going on, and you've got a bunch of certain derivatives for certain functions. So you have to be able to manage the chain rule and think about what the derivative of tan is at the same time. And then we can get some implicit differentiation involved as well. So if we were taking the derivative of this whole function, on the left-hand side, derivative of y squared would be 2y, and then the derivative of y is dy dx. And on the right-hand side, we have a chain rule. Outside function is tan, so the derivative of tan is secant squared. Keep the inside the same. Multiply by the derivative of the inside function. To get y prime by itself, I guess I should have asked for y prime. I'm going to write that 7 out in front, because generally if we're multiplying by something, it's easy to see it out front. Divide both sides by 2y. at this question, ask yourself, is this a product rule or is this a chain rule? How do we know it's a chain rule and not a product rule? How do we know that we have a function inside of another function? Okay, so we're saying that the sine of x is inside of tan. What would this look like if it was a product rule? Product rule would look like this. Can you see here the sine x isn't inside the tan? It's just tan x times sine x. Whereas the one that we have, the sine x is inside of the tan. So how do we go about a chain rule? Derivative of the outside function. The outside function is tan, which will be secant squared. Keep the inside the same. Multiply by the derivative of the inside. It's the derivative of sine, positive cos or negative cos? Positive cos. Okay, here we could use the quotient rule, or we could bring that function up to the top. If I bring that function up to the top, I would have 3 bracket sine of 6x to the negative 5. Now it says that this question has the chain rule twice. Can you see that the 6x is inside of sine? Can you see the sine is inside of a power? So we have to do the outside function first. What is the outside function? It's that power of negative 5. That negative 5 would come out in front. Keep the inside the same. Subtract 1 from the exponent. Oh, I'm going to run out of room. There we go. Step 1, derivative of the outside function. Kept the inside the same. Now we have to do the derivative of the inside function. The inside function is sine of 6x. What's the derivative of sine of 6x? Well, it's another chain rule. What does that mean? What's the derivative of sine? Cos, keep the inside the same, and then multiply by the derivative of the inside. So we've used this language every time I talk about the chain rule. I use this language. Derivative of the outside function, keep the inside the same, multiply by the derivative of the inside function. So here, my outside function first was the minus 5. Did the derivative of that, the 5 came in front, subtract 1 from the exponent, kept the inside the same. And now I'm doing the derivative of the inside, which is another chain rule. So now my outside function is sine, and my inside function is 6x. The derivative of sine is cos, kept the 6x the same, and then multiplied by the derivative of the new inside function, which is multiplied by 6. We could have some fun putting functions inside of functions inside of functions inside of functions over and over and over and over and over and over and over again. And your derivatives just get longer and longer and longer and longer and longer. Chain rule twice. Okay. Find the derivative of tan cubed x. I'd like you to try this one on your own. write the answer down here. How did you do? Maybe you wanted to take the time to start off with by rewriting this like that. That helps to see that the outside function is the cubed and tan is inside. Other questions we've done in the past are finding the equation of a tangent line. So remember, what do we need for an equation of a tangent line? We need the slope in one point. We want to find the equation of a tangent to y equals sine of x at the origin. So we know the point is 0, 0. We just need to find the slope of this line. Remember, our derivative finds us all of our slopes. So if I find the derivative dy dx, that will equal the slope of my lines, of all my tangent lines. The derivative of sine is cos. And we're finding specifically when x is equal to 0. From your unit circle, do you remember what cos of 0 is? Right? Think about the angle of 0. That's going to be the coordinate 1, 0 because it's a unit circle. Is cos your x coordinate or your y coordinate? Cos is your x coordinate. And so your slope would be 1. So once you have your slope and your point, I think this one works really well to use y equals mx plus b because the origin is your y-intercept. Slope of 1, y-intercept of 0. The equation of the tangent line will just be y equals x. Oh yeah, another one for you to try. It's a show that question. Hint, it's got a cos 2x. You're probably going to need to use one of your identities. First of all, checking your derivative. First step in the derivative, chain rule, the 3 comes out in front. Keep the inside the same, subtract 1 from the exponent, multiply by the derivative of the inside. Minus the derivative of sine x is cos x, so the derivative of minus 3 sine x will be minus 3 cos x. Now, in a show that question, where you want it to look like this, often the answer provides hints of what to do next. In this case in particular, it's really hard to see what to do next. But the fact that I see that this is all multiplying, and I have a minus 3 cos x times cos 2x, I'm just going to see what happens if I factor out a minus 3 cos x. Because if I factor that out, it might turn into something that matches up. At least that part of my equation is the same as that part of the equation. Well, if I take a minus 3 out, I'm left with minus 2 sine squared x, and then plus 1. And if we look up on the wall, sure enough, 1 minus 2 sine squared x is cos 2x. And we're done. So looking at the answer for a hint of what to do next is a good strategy in these situations. I see the minus 3 cos x in front. I didn't know if that would actually help me or not, but I factored out a minus 3 cos x, so at least that part matched up. Yes? Oh, so right here, we have the 3 formulas for cos 2 alpha. Survived. So if I rewrite this one as f of x and that power of 4, for the time being, it's sometimes a lot easier to see which is the outside function when you rewrite it like this. Can you see the 2x inside of tan? Can you see the tan inside of the power of 4? So we have tan inside of 4 and 2x inside of tan. This will be the chain rule twice. The chain rule always starts off with the derivative of the outside function, which is the 4. Keep the inside the same, still tan 2x. Subtract 1 from the exponent. Multiply by, now we do the derivative of the inside function. What's the derivative of tan 2x? Well, the outside function is tan, so the derivative will be secant squared 2x. Keep the inside the same. And now we have to multiply by the derivative of the inside function times 2. You could derive each of these other trig functions if you wanted to. For example, if you had f of x equals cosecant x, you could change that to 1 over sine x, which is the same as sine x to the minus 1. How do we do the derivative of sine x to the minus 1? It's a chain rule. The minus 1 would come out in front, subtract 1 from the exponent, and then multiply by the derivative of the inside function. This would give us negative 1 over sine squared x times cos x. And that's the right answer. You could leave it like that. Can you see that they have decided to take that sine squared and write it as sine x times sine x, because that would be sine squared x. And 1 over sine x is negative cosecant x, and cos over sine x is cotangent x. And that's how it's written in this form. But it would have been fine to leave it as cos over sine squared x. I personally don't memorize these ones because I always just change them to sine and cos and figure it out. But it's not bad if you want to. I find the cotangent one is not hard to memorize. Since the derivative of tan is secant squared, the derivative of cotangent negative cosecant squared isn't that hard to memorize. And so if we use those formulas, the derivative of 3 cotangent x will be negative 3. Wow, that's not even close to the letter C. Negative 3 cosecant squared. And the derivative of cosecant is negative cosecant cotangent. So here we have our derivative. I'm going to add one more example just to add something that feels a little bit different. Let's do cosecant of tan x. So from your formula, your derivative of cosecant is negative cosecant cotangent, okay? Which is different because there's two x's in the derivative. So this is what I wanted to point out with this chain rule. How do we do a chain rule? Derivative of the outside function first, keep the inside the same. So our derivative here would be negative cosecant tan x, cotangent, tan x. That's the derivative of the outside function. Then you multiply by, thank you, the derivative of the inside function, which is tan. So we would multiply by secant squared in the end. The rules stay the same, just the data management gets complicated. Can you see that I did the derivative of cosecant by just doing negative cosecant cotangent of whatever was inside? Then after that, I multiplied by the derivative of the inside, which is just secant squared.